What is up, everybody? Welcome back to my channel. This is Tony, aka One Lead Code One Day. If you're new here, this channel does one lead code per day, following the pattern of topics or series. That is, I'm going to be solving with you together on a lead code problem I've never attempted before. You heard that right, there's no prescripted answer, and we're on the same page here. But don't you worry, I got you covered, and I promise that I will submit at least an average performance code at the end of each video. Here's a little bit about myself. I come from a non-computer science background, so I'm no better off than most, if not all of you guys, in terms of coding knowledge. But that is okay. If I can do it, you can do it. It's all about learning on the go. You can think of this video as a first-person gameplay of cracking lead codes. And who doesn't like first-person gameplays, right? So without further ado, let's start today's coding problem. Today we continue on series 1, everything about dynamic programming, and the problem is 1014. Best sightseeing pair. Let's get into it. All right, best sightseeing pair, medium. You're given an integer array, values, where values I represents the value of the ith sightseeing spot. Okay, sightseeing sounds interesting. Two sightseeing spots I and j have a distance j minus I between them. This starts to sound like the traveling salesman problem because there are spots and they have distances. And the score of a pair of sightseeing spots is values I plus values j plus I minus j. That is the sum of the values of the sightseeing spots minus the distance between them. Right? Makes sense. So each sightseeing spot has like a sightseeing value, but also uh, there is a cost between them, right? Like the distance between them. Return the maximum score of a pair of sightseeing spots. Okay, so it means you have an array of sightseeing spots and you want to pick two of them, whose combined value is the maximum. Makes sense. Like if you have like a holiday and you have a few spots in your mind that you want to visit and you need to pick two, right? You want to pick the two that has maximum value and are not too distant from each other. So you can, visit them maybe within a weekend and then, uh, you know, enjoy the maximum happiness. Right, example one. So, for example, these are the list of our sightseeing values, and then the first and the last seems to have the highest value, but they're too distant. So maybe we should take the first and the third because, yeah, it'll be a plus 5 minus the distance, which is 2, right? So a plus 5 is 13 minus 2, that'll be 11. Exactly, right. And second example, if there's just two of them, 1 plus 2 minus 1, it's the same as just visiting one. Right, okay. And the constraints, um, we will have a length of at least 2, right? There's going to be at least 2 sightseeing spots for you to pick. Uh, and the values are between 1 and 1,000. So they all have positive values. Gotcha. Um, I think this problem pretty straightforward. I don't know how difficult it is. Sounds straightforward. I like straightforward problems because it will make it sound easy. Now, let's just right away start a um, uh, notebook, Jupyter notebook, and start copying and pasting the, I guess, descriptions into it. Now, 10, 14. And then let's just copy the description as well as example one in there, right? Yeah. So good, got it. And then we're gonna copy basically just a solution template there, and let's just put some, I guess, put some test cases in there. For example, I'm just gonna, yeah, put some test cases in here. The first test case is this, and we're expecting 11, right? And the second test case was 1 and 2, and the answer was 2, right? Okay, so now let's start thinking what this problem is about. So we have an array, and this is about maximum. So maximum of something, it naturally brings up to the thought of, using dynamic programming. Um, and then, well, just let's, just take the face value of the problem, think about, an array and where you need to pick two values, and what would you think about that? Pick two values, right? Um, yeah, you could just do a search, but that'll be like what? Time complexity of n squared, right? Because you need to pick two values. You need to do a for loop for the first value, do a for loop for the second value. That's going to be an n, O n squared time complexity, which is unnecessary. Or, um, what if we just search once? Uh, I mean, think about it. Just use your imagination. Think that you can spend like a 2-day holiday, a couple of days of holiday somewhere, and you have a list of destinations, sightseeing destinations to choose from, and you're gonna be now judging in your mind where do you want to go, and you can go two places and two places only, and you're gonna be calculating their distances, right? Um, then maybe you're gonna be, you know, scoring them, and should try to calculate the cost effectiveness, right? And right, maybe we're gonna just start using subproblem, uh, in a DP fashion. Let's say we start with just the first two sightseeing spots, right? And then, maybe your wife, your husband, your girlfriend, your boyfriend, it's gonna come up, hey, say, with how about this, right? And then they just gonna add one value into your existing, uh, add one spot into your existing pool of sightseeing locations, and then you're gonna see, hey, if that new place is gonna add uh, 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 actual additional value to our existing pool of locations, right? And then they come up with another one, and then you're gonna say, hey, is that gonna be uh, creating some new opportunities or not, right? So yeah, I think I got this. I think we can start now thinking about a dynamic programming type of heuristic. So uh, just think DP, okay? Right. So what do we do when we think DP? The first thing what we do when we think about DP is what is a trivial uh, minimal problem, right? And then also what is the definition of a subproblem, right? So for us, a trivial minimal problem is like when we're given only just two locations, right? And then definition of a subproblem, well, a subproblem mm, 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 is the subproblem. Okay, the subproblem, a subproblem is the is finding the maximum uh, uh, value pair, maximum value pair of destinations of spots. Yeah, let's say indices. Yeah, in the current subarray, right? In the current array of spots, right? So the first subproblem we're going to solve is this, and then we're going to build from the bottom up, and then we're going to go to 815, right? And then we're going to try to solve the problem of use the result of this subproblem to solve the next subproblem of 8152, right? And then we're going to solve the original problem, which is the largest subproblem in our in this list, which is 8156. So we're going to return values for all of them. So how do we do this, right? Uh, I need a strategy. Like, how do you come up with? So from this to this, the only thing we need to do is to see um, if the newly added value at the end of the array is going to add any value to our existing solution, right? So how do you do that? And then so the next question is what is the recursive uh, uh, relation between value of a subproblem and the value of the next subproblem based upon the first, the previous subproblem, the values, right, between, right. So let's just start using some symbols, okay? Um, for example, I'm gonna call this subproblem. Yeah, how do you label them? Um, because you have one, two, three, four, five elements in the original problem. And then now we're starting from one and two, right? So we're gonna call this subproblem uh, S of, let's say S of one, because why? Because the second index is one, and this is going to be called S2, S3, S4. So the recursive relationship is we're trying to ask ourselves, what is S2 in terms of a function of S1, right? Um, well, in S2 we have a new value. S1 is trivial, so it'll just be a plus 1 minus the distance between them, so it'll be just 8, okay? Um, the value. S2 value will be, if we already know what's the maximum value in here, then right, if let's just try to theorize this and write down some assertions, right? So if the new value, if the new index added at the end of a previous subproblem is going to bring any new opportunities at getting a higher what? Higher uh, m- maximum value, then it has to be used. It has to be included, right, in the maximum maximum spots pair, right? So this is obvious. Like uh, if the new addition is going to create anything better overall, it has to be included, right? So we're gonna have to just find out which one of these previous indices is going to be combined with this number 5 here. So do we know that? Uh, does it have to be combined with one of the two values we selected before? I don't know, honestly. Like, if previously the two spots were like just next to each other and they're just at the beginning of the array, but very distant from the new value, then that's a really bad situation because we might have to ditch the entire selection previously and then just pick something close to actually the new index, right? So the optimal answer is not necessarily going to involve one of the previously selected values. It's not. For example, if we have, yeah, just for example, if we have like this case, right? A um, one, let's say we have a 1 1 1, and then here we have a, let's say, 4, right? Previously, if it was like this, we're still gonna take a and 1. But then now with an addition of like a 5, now suddenly taking 4 and 5 is the better choice. So we will ditch the previous ones altogether. So it's not true that um, the new optimum maximum pair is going to include one of the previously selected spots. So but that doesn't hold. So the question is then, how do we find how do we find uh, the next pair? How do we find the next pair, right? How do we find the one value that has good value for this? Oh, I see. We can, you know, uh, I think I just found a good intuition for this. So although, like, right, although we don't know if the previous selected maximum is going to be included in here, but we can prepare these values for their potential value to be combined with the new value, right? For example, what's the potential value of this if it's combined with this? And what's the potential value of the second one if it's combined with this, right? So, because let's say this is k equal to This is what k equal to 0, 1, 2, 3, 4, 5, 6. K equal to 6, right? So if any value in between these are to be combined with 5, um, so the value that any of these values can provide is going to be, the nums of k itself. Now the k means like the index of one of those, right? Um, um, and then now we're going to have to account for the distance to this value. So minus, right, the distance minus distance to the distance from k, right, to the new guy. So which is like the uh, from k to, let's say this is the length of the current array, right? Like let's say that, this is the, we have in total, like, let's just change a few notations here. Let's say our new thing is, uh, okay, we'll say if this is k, but then inside here, we're going to use a different value, okay? Let's say we're going to pick the mth element, sorry, index m, right? So, for example, we pick this, and m equals to 0, 1, 2, 3, right? So the potential value of this index 3 uh, location to a future potential new addition after the current subarray is, this is like 0 to is like k values, right? K values. So the will be distance from m to to k, right? That's like the yeah the potential uh, value add to the next to the next uh, to the next sightseeing spot, uh, uh, to the new, right, to the new sightseeing spot at the end of the subarray k. Yeah, so this is a potential value add. So we can use a memory to basically remember, the potential value add to the new sightseeing spot at the end of each subarray by calculating this, right? So we're building these tables because these things, they don't change. Uh, they don't change, and then you can just expand this table, expand this array, and then you're gonna see, right? And then we're gonna just keep a maximum. Yeah, memorize memorize the memorize the best index, memorize the index in the current subarray with the best potential value add, right? Right. And then we're gonna roll forward. We're gonna memorize the index because this index, right? This index doesn't change um, that often, right? It's almost a static value. Yeah. So this index stays pretty static. Stays static. Uh, uh, Stays static. Like not most of the time, but stays static uh, until a new value added to the array subarray defeats it. Yeah, defeats the previous one. Defeats the current one. So it's like, yeah, it's like gonna be like a incumbent champion, right? We're gonna have like a uh, best potential value, right? So we're gonna find, index. Let's give it a name, index of the best value add. Right. We're gonna find this index of the best value add. Uh, how should we name it? Let's name it um, ind BVA. Okay, ind BVA. All right. So we're gonna keep this as a memory, keep this in memory, and then we're gonna grow our subproblem larger and larger in this fashion. Right, we're gonna let's just say keep uh, memorize memorize int BVA, grow subproblem, uh, and then yeah, and then update the maximum max value pair max pair value, yeah, max pair value. We're gonna call it max PV, right? Max pair value, max PV, right? And then until we reach the end, until we reach S, it'll be n minus one, right? So this is our dynamic programming formulation. Hopefully it's because the problem is straightforward, the solution is simple too. So we're just gonna uh, sit on this series of insights, intuition that we've built and start solving it. So um, we're gonna have like just call our version one as a DP bottom up, DP starting from the leftmost two elements, right? And because it's a bottom up DP, it'll almost certainly involve a for loop, right? Uh, so let's just initialize best value add, initialize our values a little bit, uh, and what else? So max BV, max value pair, right? Max value pair, max value of a pair. Yeah, index of the current best value at element, right? Now we're gonna use, yeah, let's just take n at the beginning of this. N equals to length of nums. Is it nums or values. And let's just say if n equal to 2, we're not going to do anything below, and we just return the sum of values. Okay. And then so for when n is greater than 2, we're going to start the for loop and then we're going to start from our um, most trivial problem of the first two elements. So for k in range of n, right? But just wait a second. Since our k actually starts from the third element, right? Yeah. So we're gonna say range of 2n. K is the current new element added to the subarray, right? The subproblem. The subproblem as k minus 1, right? Yeah. So first, the current subproblem is S1, and then you add k equal to 2 into it. And then, so what is our recursive relationship, for example, now? So now S2, let's go back to S2. Um, what is this value? So we know that we already have a max, right? Basically, we need to update this max PV. So this max PV, we're basically gonna use this int BVA, right? Um, we're gonna add this int BVA. Let's say if int BVA, the value at int BVA plus plus the value at k, if this is greater than max PV, right? Then we're gonna take the new the new sum, the new max, all right? If otherwise, we're gonna just take the previous max PV. So that means there's no change, max PV, right? And then in the second case, we're going to, well, in both cases, we're going to update. Then yeah, we're going to update and best value add. Of course, we'll update max PV as well. So with that being said, it's going to be like an if condition, right? If values of int BVA plus values of int at int, let's say k, right? If this is greater than the current max VP, which is initialized as what? Sum of like right, just values 0 plus values 1 minus 1, right? So we're going to initialize max value of a pair. And what is the initialization value of int BVA? So for the first two, because the BVA is going to be this minus this, right? Uh, right, so we can further expand this expression as um, n of m minus, so the distance between m and k is simply k minus m. Is that right? K minus m. So for example, between 3 and 6, the distance is 1, 2, 3. Or is it 3 or is it 4? Yeah, let's just see the description. Ah, distance j minus I. Okay, okay. So yeah, it'll be just this, like, right, uh, minus k minus m. So it'll be, yeah, nm minus k plus m. Simple as that. So uh, we're gonna just uh, 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 take the maximum, right, of the first couple of it. Can we, let's see, n minus k plus m. Can we build a function for it? Yeah, we can. Um, can we build a function for it? Well, yeah, let's just use the function self. Mm, uh, uh, self compare BVA, right? Compare BVA between two indices. So we're gonna have to provide, you know, int1, int2. We're gonna also provide, the k value here, which is, the length. Well, yeah, the length of the subarray we're talking about. So the values, we need to send this in there, right? Right. So if we're doing this, let's just first return 0 or something. Now def compare BVA, which is a new function, and we have values k int1, int2. What this is, we'll have a description. Compare or return the better index after comparing the best value add of two indices, int1, int2. Uh, uh, let's say in the array, in the subarray of what? Yeah, in the subarray of values, right? Values 1. Um, yeah, let's not send like a huge array to the function. We just send what we need, okay? So we're gonna send values, the beginning all the way up to, k. That'll be k plus 1, right? In this case, it'll be 0 to 3, right? No, to 2, right? That's where you want to go. You want to compare the first two. So gonna be, the array, right? Yeah, and a subarray called array. Let's just call it subarray, right? Give it 3 more letters. We can afford that. And type subarray. It's a list of integers. Um, type int1 is an integer. Type int2 is also an integer. Return type is an integer as well. Yeah. So we're going to return either the first index or the second index. And we're just going to be simply calculating the 2 equations of this, nm minus k plus m. So we're going to say n equals to the length of the subarray, okay, and the best value out of 1 is going to be subarray value of int1 plus minus k plus m. In this context, k is the length of the subarray, so minus n plus what? Plus the index of the current candidate, so int1. So bval bva2, right? Yeah, let's just use underscore to separate the characters with the number. Subarray int2 minus n plus int2. So we have them. The next thing left is to compare them, right? So return int1, and we're going to use a list comprehension, something like that. Int1 if bva1 is greater than bva2, else int2, right? So that's the thing we're gonna do. But I'm not sure if this is actually the right expression. Let me just be safe and Python list comprehension if. See what's the expression. Right. Or should I ask Python, what does list comprehension return? Are used for returns lists. They can they consist of brackets containing expression. Okay, so list comprehension is going to return a list, right? So if we're going to just return the first element in the list, shall we do that? Can we do that? I don't know. We'll try. I mean, if it doesn't work this way, we'll just use the easier um, yeah do it in the easier way. Now, how about we just test the list comprehension, right? Yeah, so s equal to solution, and then we're going to say s dot compare, compare BVA. We're gonna try, let's say, just some random lists, okay? And then index, the first index is gonna be, let's try 1. Let's also try 3, and then see what it returns. Well, we haven't defined anything yet, so it'll say no definition. Okay, now let's try. Does it return anything? It seems like it did not return anything, did it? I was somehow asking it to actually return something, but okay, let's see if I remove that, and what does it return? Oh, max VP. Okay, okay. Let's just do that. And do nothing, right? Return 0. Expected an indented block. Let's say, return 0. Just put random stuff over there, and let's see if it returns anything. Okay, it returns a value. Now, what if we just say we want the first element in the list? See if it works. Yep, it does. Okay, fine. So this expression is fine. So now let's go back to the main function, and we're gonna see, yeah. So now int BVA is initialized as compare BVA of the first two indices, right? It's gonna be comparing 0 and 1, of course. And then now in the for loop, we're gonna be seeing um, if the values, right? Let's go back to our recursive relationship here. So if um, int BVA, the value at int BVA plus the new value, so the value add, if you add the value add to the new value, if it's greater than the max PV stored, then we're gonna say, okay, we found our new max. So we're gonna update max PV. Otherwise, we just don't update max PV. But we're gonna update int BVA anyway. So update max VP value pair. So max value pair equals let's say max value pair equals what is it? Equals this. Right. So that's it. And we also gonna update int BVA, right? How do we do that? Um, we're basically gonna do compare the values between uh, between our current, right? K plus, well, K is the current new element added to the subproblem. Okay, so we're gonna say in the context of the new subproblem, and then the existing BVA and the new one, which is K, right? We're gonna compare those, and then we're gonna assign a new value to int BVA. Right, right. This is actually pretty smart because although we have like an increase, if we grow our subproblem, then the BVA of the previous indices, they're all just gonna drop value by one because now the distance has increased, right? So we're gonna reevaluate the BVA, but we only need to compare the uh, the current best BVA index with the newly added index because that's the only things that's possible as possible challengers for the next int BVA, right? So that's that, and we update BVA, we update max VP. That's all we update during this, right? So we're gonna grow this all the way to k equal to n minus one. Uh, yeah, and then we can just return max VP. All looks good now, hopefully. And let's just try some test cases, all right? Oh, Rob, it's not Rob. We don't have a function called Rob here. Oh, something's not right. See, um, expect 11, but we got 14. Expect 2, but we got 3. Let's just work on the second case, okay? And looks like we're adding something extra to the problem. Now, we'll start the debugging process by turning on the little bug debugger. And we're gonna put our breakpoint right after the for loop. And let's start happy debugging. Okay, looks like it finished. So now let's restart our kernel. And start our debugger. And then put our breakpoint at this um, line right after the for loop. Run it and run it. Hey, why? Oh, because it didn't even enter the for loop. Got it. So if it is n equal to 2, it should be sum of values minus 1, right? Minus the distance. Right, right. So this is not the test case we want to be looking at. This is. And let's just start with a simpler test case, okay? For example, what if we just talk about A15? Um, then we're going to be expecting A plus 5, which is 13 minus 2, 11. So yeah, let's just use this simpler test case and then see if the debugger gets us. All right, here we go. Now, our total number of elements is 3, and we certainly went past this if n equal to 2. And our initial indices BVA is which one? Is is index 0 because it certainly has more value than 1 to any new spots, right? It has more combination added value, right? So we totally agree with int VBA equal to 0. What about max VP? Max VP of the current pair is a plus 1 minus 1, which is 8. That's totally correct. And then now we move into this loop here. And the first k is going to be 2, which is this third element, 5 here. And we're going to compare if value in BVA, which is value at 0. So if A plus value K is what? Value K is 5. Oh, we forgot to subtract the distance. That's the thing. I think that's the thing we're missing. We forgot to subtract the distance because, we always need to include, according to the problem definition, include the cost of the traveling distance. K, so it's going to be K minus int BVA, right? We're going to also, include that in this update process. Right, so we're going to have to fix this here as well in BVA. Yeah. Uh, there's a little bit more to this. So, you need to minus the distance, minus K. Yeah, it's a little bit subtle here. K minus int BVA. Okay. Yeah, we need to always add the, subtract the cost. Remember that, right? So with that being fixed, I don't know if it actually solves this problem. Yep, it does. Now let's see what happens if we try with this new thing here. It does work. What about this? It does work. So looks like we might have a solution here. Let's just try and submit this to leet code. Okay, that runs. Gets accepted. What about this submission? It's already taking a little bit long. It's making me nervous. Yeah, we'll probably find a failing test case. Time limit exceeded. Okay. All right. That's a pretty big one. Wow. But we're gonna just take it. And the fact that time limit existed, we have to now retrospect and think, what is the time complexity? Time complexity. We have a for loop, so it's at least n. Um, and in each of these for loops, are we doing anything that is like scales with n? Well, this addition is fine, the comparison is fine, uh, this is fine. What about this update? Well, this update values in BVAK, this update I think this update is fine, right? It's not really so time consuming. But anyways, let's just you know, special test case. Uh, very large n. So S equal to solution, okay? And then we're basically gonna print or just print S dot max score something of this very long array. Yeah, and we'll see what happens. We already have the definition. Let's see how long it takes to work out the solution. Is it gonna take like forever? 1997. Hey, it doesn't take that long on my local computer, but somehow LeetCode says it takes too long. Let's submit it again. It's probably gonna have to go through the same the same test case, and it'll say, yeah, time limit exceeded. So we're really having a really tight um, time limit here, isn't it? Well, let's just take the second one here and see how long that one is going to take. Print s dot max something. Come on. And this one here. Yeah, see how long that one takes. So for this, I'm just going to comment that out. Let's see how long this one takes. A few seconds. Yeah, it's not bad. So why is LeetCode complaining? So LeetCode is setting a really tight time constraint on this problem, huh? What are we going to do? We're going to just have to optimize our code in order to meet the requirements. So I thought this is like quick enough, but apparently it is not quick enough for this problem. Uh, do we have like a very large space complexity then? I mean, our time complexity seems to be just O(n), and our space complexity seems also fine. We only remember a few numbers, right? So it should be O(1). Can we optimize time complexity and then, as a compromise, uh, uh, make some storage? Can we trade off time complexity with space complexity here? That's the thing I'm asking. Mm, I mean, O of n, it's like the minimum time complexity we need because we have to walk through the whole list, right? I mean, we have to inspect each value somehow and operate on them to see if we have like a good pair of values to go, right? That is kind of straightforward to me. Uh, right. So I think I have exhausted my thinking here because honestly, I think I've tried my best. This DP solution looks pretty elegant, but uh, somehow LeetCode thinks it's not good enough. So let's actually just jump right into the solution and see what. Hey, there's no solution, and see what people have come up with. All right, one pass, oh one space. Hey, I know this face. This is the one pass guy. I love this guy. So let's get into it and see. Well, that's pretty simple, just a few lines. So let's take a look at his intuition. Count the current best score in all previous sightseeing spots. Note that as we go further, the previous score decrement. That's right. Cur will record the best score that we have met. We iterate each value a in the array, update res by max res cur plus a. Okay, yeah, we're gonna see if uh, our current best score plus plus a new value is gonna beat the current best. Also, we can update cur by max cur a. Note that when we move our all sightseeing spot, we have seen will be one distance further. So the next sightseeing spot, cur equal to math dot max cur a minus one. There's a feeling that a neighbor, a near neighbor, is better than a distant cousin. Right. That's a nice proverb there. So Python, what do we do? Cur res 0 for a in a. We update uh, res with max res and cur plus a, right? With each addition, when we meet like a new spot down the line, we're going to compare the current maximum and current global maximum of the value, the pair value, and compare that with what mm, the current depreciated, value plus the new value. And then we're going to update cur with a depreciation of -1, right? That makes sense. And then you just do it for everything, and then you do it. Yeah, this is pretty elegant, I think. More or less, we're in line with what this guy is doing. Um, but his code is just more elegant than mine, definitely. So let's just try to submit his code instead and see how fast that is. Let's just first run code, run test. Oh, run test cases. Works. Submit. Accepted, and the code is pretty fast. Okay, that's good. So what can we learn from him and absorb from him? So he uses a res to represent the global maximum. So his res is basically my max PV, right? And his cur, what is the equivalent in my definition here? Uh, his cur is um, max cur in A -1. So let's just take a look at his description again. What is cur? Um, so count the current best score in all previous sightseeing spot. Note that as we go further, the score of previous spot decrement. Um, cur will record the best score that we have met. We iterate each value A in the array A. We update res by the max between a recorded maximum and cur plus A. So cur is already like depreciated and ready for this comparison, right? Right. So the only difference between cur and res is that cur is like mm, cur is um cur is so the only difference is that cur is something in between. So cur is something between a wait is a maximum between. So A is a single value in the array, right? And when you take a max between cur and A, it's almost saying that this is like a current like it's not a pair, it's not a value of a pair, it's just a value of one. Right, it's like yeah, it's almost like yeah, it's almost like our int BVA, best value add, like one spot, right? The one spot. And while he is saving Well, he is saving it as the actual value. I am saving the index of that value, right? Index of that. So I'm updating these two values. He's updating that two values too. But I mean, the difference is that I'm updating the index and he's updating the value itself. Does that make a difference? I mean, there's a for loop, right? I'm updating max VP using an if condition. For him, um, he's using a max. So there's a max, there's no if condition. Can we save some time by for example, if that is greater than that. Yeah, can we save some time by just saying max VP equals to the max between this and this? Like, yeah, we're just saving some if conditions, right? So this is update max VP, right? And this is update, whoops, this is update our index for the current best uh, uh, spot candidate that we add to the next value. So in principle, I mean in spirit, the two things that I'm updating is not that much different from the two things that he's updating. But of course, his solution looks much more elegant. And while I am trying to update the index myself by coming up with a function and then performing these like performing this by using like a another helper function and then comparing these indices. What he's doing basically, he's saying, hey, we just need to compare the value itself of the best value add, right? And then we prepare it for the next round by -1. So can we do that too? Like, can we, instead of saving and BVA, can we just say like BVA, right? Can we just say BVA? Um, but then, you know what? We still need to find an index to it. So how does he solve that problem, right? Cur plus A. Oh, it's encoded in the cur there already. Because right. Because because any of those indices, if you think about it, any of those indices, it was embedded into what into yeah, because well, if you say BVA, you are already merging, the index value, the index value, uh, and the cost of the distance into the value itself. So it's like an all-in-one kind of scenario. Anyways, let me just see if this actually works. Yeah. So we're gonna do a version 2, okay? We're gonna do a version 2 based on our learning from the one-shot solution guy. So version 2, level 2 elements, um, you know, with learning from uh, uh, um, the top discussion answer. So the change here to our code is instead of uh, storing, memorizing int BVA, we directly memorize BVA, right? So when we directly memorize BVA, uh, then at the beginning, BVA is going to be just, uh, let's say, so it'll be just current best value at element. So it'll be zero, either 0 or 1, right? So which one would it be? Will it be will it be 0 or will it be 1? I mean, it'll be, if it's a zeroth element, it's going to be the content in the zeroth value, um, and then minus the distance between this and the next potential added value. So it's going to be the max between what values 0, values 0 minus the distance between 2 and 0 will be 2, right? And then values 1 minus 1, right? Current best value add element, max VP, initialize max value of a pair, right? And then for k in range, we're gonna do max of what values BVA. We're just gonna say BVA plus values, right? We don't need to minus that because this distance is already accounted for in BVA because the best value add includes the cost as well. And then now when we update BVA, uh, it'll be like between a comparison of the best value add of the current BVA as well as the new challenger, right? So it'll be like a max between BVA and um, values K, uh, values K, and because values K will have a BVA I think it'll be minus one, right? Because, at the end of the day, when you move on to the next iteration, you need to depreciate, the value because the distance now increased. Max BVA, and then this minus one. Yeah, yeah, yeah. I think so. So now return max VP, and now you don't need this function at all. So let's just try this, okay? Yep, we got the same solutions. Uh, but you know what? Maybe instead of for loop looking up the indices, we can just look up the array element itself. That'll save maybe something. Just load the entire array into an iterator instead of trying to do the index because each time when you're looking up the index, it's going to take time. But anyways, I think this is already better than our original version 1 code. So I'm going to submit this, see if it passes the time limit by eliminating some of the things. Yeah, it's okay-ish, but you know what? We could optimize. So by optimize, I mean maybe instead of using for loop to look up using for loop for indices, if we replace, yeah, version 3, let's actually do a version 3 here. Version 3, uh, so performance optimization, right? Replacing index iterator with array element iterator for performance, right? Uh, so the time complexities of, and you know, I was hoping like the space complexity of all of these problems are like O of 1, but somehow there's still a difference. Anyways, so now what we do in this, now, instead of say K in that, we're gonna say now V in values. And because we're starting from this, from the, yeah, from the third element onward, we're gonna do values plus V, and this is like V, right? Yeah, yeah, yeah. Update BBA. So let's try it. Yep, it's gonna be like this. So hopefully this is gonna be faster than our previous one, right? So let's just run this a couple of times. So this is like 30%, 40%, right? 60%, 50%. So it's on average like a 50%. Wow, this is even better. Okay, let's submit again. Yeah, so on average like a 50, 60%. So now with this new version 3, which is like a performance booster, let's see how that goes. Yeah, upper 70% now. Let's try it again. Yeah, 50, 40, 40, 40, 70, 40. So maybe it's a little better, but okay. Yeah, we have those things here. Um, but somehow if you look at the solution of this guy, you'll realize that he doesn't even need the initial cases, right? Um, it's so elegant that it's just this. Uh, and how are we going to generalize it into that? Well, that means we're gonna have to use the full values list. And then can we do that? Because now the first value V will become just V, right? And BVA, best value add, we initialize, in this case, we initialized it with this. But what if we start from the first element? Then the best value add. Yeah, we can afford to start with some zero because eventually this is going to grow, right? So now let's just try our next version. Version 4, version 3 is replacing on version 3. So version 4 is like removing special cases in version 3 just for improvement of speed, right? So now we're going to use the full values list. And then BVA, instead of initializing it with that, we're just going to initialize it with 0. Um, what about max VP, right? Max VP, if we're starting from the first element, the max VP is gonna start from 0, right? Um, right. And so we're gonna remove this special case consideration. And so now let's see. When we're taking the first element, BVA starts at 0. V is gonna be the value of the first element. And this is 0, so it'll probably be just V itself. And then BVA, it's gonna update itself as 0 or the first value. Yeah, it's gonna be the first value minus 1. So it's already good. I think it's already good. Yeah. And then when V comes to index 1, so the second element in the values list, now max VP is gonna be comparing BVA of the previous value, which is basically just value of the first of the index 0 uh, minus 1, and then plus the current value, right? That's already a correct calculation. And then max VP stored before, which was, yeah, like before it was just the value of the first spot, sightseeing spot, which is still okay. And then we're going to update BVA between the of the as the max between previous BVA and the current V, and then minus 1, which is also correct, right? You just have to depreciate it once more to prepare it for the next uh, iteration. So I think everything's good, and we're gonna have a good solution. And let's just submit this to the code as our version 4, and yeah, it's gonna beat everything. It's not beat everything, but it's as good as an average code. And I was just curious because I saw something even better here, like a one line solution here. Python one line. Look at that. Wow. Just look at that. I mean, this definitely takes some skill to write everything here in just one line. You basically just uh, packed this into one line. This is definitely something we could learn. I mean, when we go along with this and we found ourselves uh, more skilled with code, maybe we can one day just use one line to solve it. So yeah, I'm gonna store this version 5 here. Um, version 5. Let's just say someone else's code, one line. I mean, this is just badass. So I'm going to take it. Uh, let's just try it, okay? Whoops, there's something wrong. Oh, lambda. Um, what? Why is this lambda? Let's try. Invalid syntax. Hmm. Why is it wrong here? Is the lambda expression wrong? I mean, I don't know. What are we missing here? Let's see. What are we missing here? Invalid syntax. So lambda function, there's something wrong with your lambda function expression here. Uh, yeah, is anyone talking about the lambda function here? Nobody knows. So I'm going to, let's say I'm going to type comment here. Yeah, I'm going to just copy. Um, I tried the one line Python solution
but got some error. Can someone point out what is wrong? Yeah, the one-line solution. So I need to, basically post some code here. Can we post code? Um, Preview. Right, so this is, I guess, and I got this error. Let's see if we can just, right, copy and paste everything here and send it here. Let's preview. Right, okay. Let's post it. All right. So I don't know what's wrong with that one-line solution, but I think we're good today, right? So although our initial submission didn't work because time limit exceeded, it doesn't mean that it's wrong, but it's just that we're not meeting the requirement, the performance requirement. Then uh, we realized that with our current intuition, maybe one place where we can improve our performance is to instead of yeah. So let me just gonna type the learning here. Fill with the red or purple. Yeah. Instead of storing int BVA, store BVA itself, right? This improves performance, right? So after all, our initial attempt was not wrong. It's just not fast enough to uh, go past the lead code checker. It still has like a time complexity of ON and space complexity of O1. It's just that we didn't do good enough. So we learned from this guy on lead code. Let's just take a look at his name. We need to remember this guy's name, Lee 215, right? So we took uh, some help or inspiration from him, and then we improved our code. Yeah, and we did our version 2. So difference between our version 1 and version 2 is that instead of now remembering the index of the best value add, we're just gonna remember the best value add value itself, and then use that to update uh, in in the for loop for recursion. So that code worked, and it passed the lead code checker. And in the third version, we've tried to further improve the performance by replacing the uh, index in the array in the list with the element in the list, because then we don't have to look up the value by the index each time in the for loop. Hopefully that saves some time, right? And then further we try to remove these special case considerations by generalize these special cases into the general cases, and that's what we that's what we come up with in version 4. This is pretty similar to Lee 215's solution in here, and yeah, we had an okay-ish, actually above average performance right there. Uh, so this is today's video and summary. Thank you guys for sticking along, and I'll see you in our next video. Peace.